So here we are going to discuss how electrical activity in the heart regulates the heart function, how it regulates the contraction, and also then automaticity of the conducting system that is enabling the heart to work on its own, but the automaticity can be regulated by sympathetic and parasympathetic nerves. So let's start with the action potential on the cardiomyocytes, on those contractile cells that are able to eject the blood to aorta or to pulmonary artery. So first, let's have a look at the structure of cardiomyocytes. You see that these are single nucleated cells that are branching, unlike skeletal muscle, but otherwise the apparatus is involving actin and myosin, and the sliding of actin and myosin during the contraction is similar. What is unique for the cardiac muscle is also existing of the connections between individual cells through intercalated discs that have two things, gap junctions through which ions can easily flow, and so the cells can easily communicate and change the membrane potential and electrolyte content, and also desmosomes, which are holding the structure, the network of the cells together. And so this is mainly for the mechanical purposes. So the action potential on the heart differs from action potential on neuron or skeletal muscle. You see that mainly it is a question of duration, and this shape the plateau, which is very important for the muscle contraction. So what's happening in the cardiomyocyte is that at a resting membrane potential at the phase 4, the only channels that are open are potassium channels, and when they are going out of the cytoplasm, they are making the already negative. They are maintaining the negative membrane potential, and they have a tendency to leak from inside to outside. But now when a stimulus arrives, the stimulus will come from conducting system and to the cardiomyocytes that are connected with conducting systems through those gap junctions. The sodium channels open, and you see that sodium channels are fluxing in because there's a lot of sodium outside of the cells, but very little sodium inside. Also, sodium is positively charged electrolyte, while the inner part of cytoplasm, the membrane is negatively charged. So these two forces are practically sucking the sodium in, and you see that very quickly the membrane potential changes, and the cell membrane from polarized state changes to depolarized. Once it's depolarized, the depolarization activates voltage gated. There was change in voltage, so voltage gated potassium channels. But shortly after that are also activated voltage gated calcium channels. And this is unique. And this plateau here is what is absent in the neurons or skeletal muscle. So what's happening during this plateau is that calcium moves in. At this voltage-gated calcium channels are open, and calcium moves in. And we call this calcium-induced calcium release that will be important then for contraction. So calcium comes in, and because now we are at positive positive voltages, and calcium is also positively charged, there is a delay in the repolarization. Then the calcium channels close, and only the potassium channels are open, and potassium is leaving the cytoplasm and goes to the extracellular space. So that makes the removal of positively charged potassium starts restoring the electrical negativity on the membrane. Now, remember, we were talking about skeletal muscles, and the skeletal muscles have also here the sodium-potassium pump, so does the heart has. And sodium-potassium pump is an ATP-consuming pump that is required for restoration of sodium-potassium. Sodium needs to go out, and potassium needs to move in. So that pump that restores the membrane potential with regards to the electrolytes is very dependent on ATP. So this is our shape of the membrane potential on cardiomyocytes. And remember, the big difference is that there is the voltage-gated calcium channel opening that causes the influx of calcium during the action potential. So here you see the same figure, just did a little bit different diagram. And now the calcium influx here is key for the contraction. So here you see the change of membrane potential and the T-tubule, those invaginations that surround the contractile apparatus. And the calcium is important for this particular receptor that for getting into sarcoplasmic reticulum and release the endogenous calcium. And now, why is calcium critical? This reason is same as in skeletal muscle, and it basically enables reaction of actin and myosin. So this is depicted in this picture. You have here an actin, the brown. Here we have the myosin, and the actin is surrounded by a molecule called tropomyosin. And the tropomyosin has some other proteins there called troponins. And when the muscle is relaxed, the tropomyosin tightly winds around the actin. But now when calcium comes, the calcium changes the conformational position of troponin. The tropomyosin is more relaxed. And now you see newly those blue dots here, which are the myosin binding sites on actin. And when this happens, then these heads of myosin can now bind to these binding sites, and the actin and myosin can slide, and contraction occurs. So, we know that in cardiomyocytes we have this plateau. We have the different mechanism of contraction because it's regulated by calcium, so called calcium-induced calcium release. And now, how come that the action potential actually occurs at the cardiomyocytes? So the answer is in having the conducting system that starts with sinoatrial node. And this conducting system in the heart is having so-called funny channels. More scientifically, there are HCN channels, or called hyperpolarization activated cyclic nucleotide gated channels. And what do they do is that the channels are opening and closing, and they are allowing, when they open, they allow positively charged um, electrolytes, mainly sodium and some potassium, to flux in. And now when you are bringing positively charged electrolyte from extravascular space to cytoplasm, to the inside of the cell, the membrane potential becomes less negative. And that's what you see here, right? So this was the membrane potential. This would be if this was on the cardiomyocyte. But these unique cells in the conducting system are having this opening of HCN, funny channels, and allowing the sodium go in. And as a result, the voltage on membrane is less and less negative until it starts its threshold, and then other electrolytes are moving in. So here we have the calcium influx on the conducting system looks here, while on this side, in the cardiomyocytes, it's here, right? And then the repolarization is happening in similar way, that it is because of potassium escape. But what is the key difference is that sodium is fluxing in during the phase 4. Here we see an outline of the conducting system. So the sinoatrial node is the key pacemaker in the heart. And the signals then from sinoatrial node travels through the muscle of the atrium to reach atrioventricular node, which beats almost half of the rate of SA node. But if this is removed, destroyed, then the heart is going to beat at the lower rate. And then we have bundle His, the bundle branches right and left, and they end up with Purkinje fibers. And you see it here. Here you see the skeletal, pardon me, the cardiac muscle surrounded by the Purkinje fibers. And as I already said, the Purkinje fibers are going to connect to cardiomyocytes through the intercalated discs, which have the gap junctions. And so the stimulus from this rapidly moving, rapidly activated conducting system is now stimulating the cardiomyocytes. So we reviewed the differences in action potential in a heart versus skeletal muscle versus nerve, and said that there is a unique need for calcium to come from outside. So the membrane potential is corresponding to the influx of calcium. And then we reviewed the differences in action potential on the conducting system, namely SA node, and the cardiomyocytes. I would like to end with the reminder that all these action potentials that we have seen are reflecting individual cells, individual changes in action potentials, but and we can measure that by sticking electrodes directly to the cells. You are probably much more familiar with electrocardiogram, EKG, and the EKG is summation of all the electrical activity on the heart. So the action potential of one cell and EKG is summation of all cells, electrical activity of all cells at a given time. Okay, so thank you for your attention.